An atom is the smallest particle of an element that retains its properties. It consists of protons and neutrons in the nucleus, and electrons orbiting around it. The atomic number refers to the number of protons in the nucleus, and it determines the identity of the element. For example, hydrogen has atomic number 1, while carbon has 6 atomic number. Next, for periodic table, is a chart that organizes all known elements by increasing atomic number. Elements are arranged in rows called periods and columns called groups, which share similar properties. This arrangement helps us predict chemical behavior. An element is a pure substance made up of only one type of atom. It cannot be broken down into simpler substances by physical or chemical means. Example include oxygen and iron. Next, isotope. Isotopes are atoms of the same element that have the same number of protons, but different numbers of neutrons. They have similar chemical properties but different mass. For example, carbon-12 and carbon-14 are isotopes of carbon. Next, for molecule. A molecule is formed when two or more atoms are chemically bound together, acting as a single unit. Example include water, H2O, and oxygen gas O2. Compound. A compound is a substance composed of atoms of two or more elements chemically combined in fixed proportion. For example, sodium chloride or table salt is a compound. An ion is an atom or group of atoms that carries a positive or negative charge. A cation is positively charged because it has lost electrons, while an anion is negatively charged because it has gained electrons. For example, sodium ion Na+, and chloride ion is Cl-.
Today we are learning how to make ions. First, let's talk about metal ions. For metal ions, the rule is very simple. Keep the name of the metal and add the word ion at the end. For example, Na+ is called sodium ion and C2+ is called magnesium ion. So basically, metal names stay the same, just like ion. Next, we remove the whole atomic anions, which are non-metals. For non-metals, the naming rule is different. We change the ending of the element name to ite. For example, chlorine becomes chloride, carbon becomes carbide. So whenever you see a non-metal ion, remember element name plus ite. On to naming ionic compounds. Ionic compounds usually consist of a metal and a non-metal. The naming rule is name the metal first, then name the non-metal with ite ending. Let's look at some examples. For BaCl2, Ba2+ is barium, Cl- is chloride, so the compound is called barium chloride. For T2O, K+ is potassium, O2- is oxide, so the name is potassium oxide. For MgCl2, Mg2+ is magnesium, Cl- is chloride, so the compound is magnesium chloride. Lastly, CaS, Ca2+ is calcium, S2- is sulfate, so the name is kalium sulfate. When a metal combines with a polyatomic ion, the rules are simple. The positive metal cation goes first, and the negative polyatomic ion goes last. Notice that the name of the polyatomic ion doesn't change. BaSO4 is simply barium sulfate. If the metal is a transition metal, we must also specify its charge. Unlike group 1 or 2 metals, transition metal can have multiple possible charge. Looking at our periodic table, you can see that iron ferrum can be 2+ or 3+, while copper Cu can be 1+ or 2+. Because of this variability, we cannot name them by the element name alone. To distinguish between different charges, we use Roman numeral in parodies. In FeCl2, the ion has a 2+ charge, making it iron 2 chloride. In FeCl3, the ion is 3+, so it's iron 3 chloride. Always check the anion test when we must calculate the metal charge. Some ionic compounds, called hydrate, have a specific number of water molecules trapped within their crystal structure. We indicate this in the chemical formula using a dot followed by H2O. To name them, we use great prefix followed by the word hydrate. Let's look at some example. BaSl2 that 2H2O is barium chloride dehydrate because of the 2 water molecule. For MgSO4.7H2O, we use the prefix hepta to get magnesium sulfate heptahydrate. Molecular compound consists of 2 non-metal. For this, we use prefix to tell us exactly how many atoms of each element are present. The element folded to the left of the periodic table usually come first, and the second element always ends in the suffix ite. Using our prefix, N(F3) becomes nitrogen trichloride. For N2O, we have 2 nitrogen and 1 oxygen, so we name it the nitrogen monoxide. Note that we don't use mono for the first element, but we do for the second. Hydroacids are acids that do not contain oxygen. To name these, we follow a specific pattern. Start with the prefix hydro, add the root name of the element, and finish with the suffix IEC followed by the word acid. Applying this rule, HCl become hydrochloric acid and HF become hydrofluoric acid. Even though HCl is polyatomic ion, selenide, because it lacks oxygen, it follows the same pattern, hydrocyanic acid. Now let's look at oxo acids. An oxo acid is an acid that contains hydrogen, oxygen, and one other central element. You are likely already familiar with some common ones, such as nitric acid, carbonic acid, and phosphoric acid. The naming convention for this acid depends directly on the oxygen content of the polyatomic ion they are formed from. There is a direct relationship between the name of an oxo acid and its corresponding oxo anion. If an acid ends in IC, its anion ends in 8. If an acid ends in OUS, its anion ends in ITE. Adding an oxygen atom to the French acid gives it the prefix. Removing oxygen atom leads to the OUS suffix and eventually the hypo prefix. great example of the progression is the chlorine series. Starting with the chlorate ions, we get chlorate acids. Add an oxygen to get perchlorates and perchlorate acids. Removing oxygen gives us chlorate and chlorous acid. Removing one more oxygen results in hypochlorite and hypochlorous acid.
First, atomic mass is the mass of one atom. Most of this mass come from the protons and neutrons in the nucleus. Relative atomic mass, called AR, is the average mass of all the isotopes of an element. It is compared to 1/12 of the mass of carbon-12 atom. For example, chlorine has an atomic number of 17 and a relative atomic mass of. Calculating relative atomic mass. To find relative atomic mass, we multiply the mass of each isotope by how common it is, then add them together and divide by 100. For example, we use iron isotope, which is iron 54, iron 56, and iron 57. After doing the calculation, the relative atomic mass of iron is 55.19. The mole concept. A mole is a way of counting particles like atoms or molecules. One mole contains 6.022 times 10 to the power of 23 particles, which is called Avogadro's number. The mole helps us change between mass, number of moles, and number of particles. Molar mass. Molar mass is the mass of 1 mole of a substance, measured in grams per mole. For iron compounds, the formula mass in AMU is numerically the same as the molar mass in grams. Interconverting mass, moles, and particles. Mass, moles, and particles can be converted between each other. Use molar mass to convert between mass and moles. And Avogadro's number, which is 6.023 times 10 to the power of 23, to convert between moles and particles. Formula mass is the total of the atomic masses of all atoms in an ionic compound. It is calculated by adding the atomic masses of each element in the formula.
By definition, an empirical formula is the simplest, most reduced version of a chemical formula. It gives us the lowest whole number ratio of the different atoms present in compound. It's also important to note that different compounds can share the same empirical formula. So, how do we find it? There are 4 simple steps. First, start with the mass of each element in grams. Second, convert the mass to mole. Third, divide every mole value by the smallest number you calculate. Fourth, finally, round the nearest whole number to get your ratio. To find the empirical formula of a compound containing 40% carbon, 6.67% hydrogen, and 53.33% oxygen, first convert the percentage to mole by dividing each by its atomic mass. This gives you 3.33 moles carbon, 6.67 mole hydrogen, and 3.33 mole oxygen. Let's simplify this value into a whole number ratio by dividing each by the smallest value in the set, 3.33. This results in a ratio of 1 carbon to hydrogen and 1 oxygen, establishing the empirical formula as CH. In chemistry, the molecular formula is essential because it shows the exact number of atoms of each element that combine to make a single compound. To determine this, you first need to know the compound empirical formula and its total molar mass. Think of the empirical formula as the simplest ratio, while the molecular formula is the actual real-world version. Let's look at an example. Imagine we have a compound with the empirical formula CH2O and a non-molecular mass of 180. To find the molecular formula, we first calculate the mass of that simplest unit. Carbon 12 plus 2 hydrogen plus oxygen 16 give us an empirical mass of 30. Next, we divide the total molecular mass by this empirical mass, in this case 100 divided by 30, which gives us a multiply of 6. Finally, we multiply every atom in our original formula by 6. This transforms CH2O into Ca6H12O6.
Percent composition represents the percentage by mass of each element within a compound. It is calculated using the formula percent composition equal to N, which is the number of moles of the element, times M elements, which is the element's molar mass, divided by M, which is the compound's total molar mass, times 100%. For example, determine the percentage composition of sodium carbonate. So first, we need to figure out the total weight of the entire compound, which is 106 grams for the sodium carbonate. Next, we need to measure the weight of each element. We got sodium weight for 46 grams, carbon weight 12 grams, and oxygen weight 48 grams. Finally, divided each element weight by the total entire compound weight to get the percentage for the element. It's basically show how much of the compound is sodium, and how much is carbon, and how much is oxygen.
The technique. First, write the correct formula for the reactant on the left side and the correct formula for the product on the right side of the equation. Second, change the number in front of the formula coefficient to make the number of atoms of each element the same on both sides of the equation. Do not change the subscript. Third, start by balancing those elements that appear in only one reactant and one product. Fourth, check to make sure that you have the same number of each element type of atom on both sides of the equation. For this example, we balance the chemical equation by making sure the number of atoms on the left and right side is the same. First, we count the atom for carbon, hydrogen, and oxygen. on both sides of the equation. Then we adjust the number in front of the compound until every element match. When the number becomes uneven, we multiply the whole equation by 2 so that all the values were whole and equal. After balancing all the atoms, the final equation becomes 2 molecules of methanol react with 3 molecules of oxygen to form 2 molecules of carbon dioxide and 4 molecules of water.
How to do stoichiometry calculation? First, we need to ensure the equation is correct and balanced. Like 2H2 plus O2, we got 2H2O. Next, we need to identify molar ratio. Use coefficient for mole-to-mole conversion factor. Then, we know H2 got 2 mole and O2 got 1 mole. Next, we need to convert given units. Use molar mass G per mole to get moles. Then, apply ratio. Use the molar ratio to find moles of the desired substance. Then, convert to desired unit. Convert moles of the desired substance to grams. Use molar mass. Example. First, mass to mass. O2 to H2 in 2H2 plus O2, we got 2H2O. The problem right now is how many grams of H2 are needed for 54.0 gram O2. First, we need to search of mole O2. We use 54.0 gram divided by 32.0 G per mole equal 1.69 mole. Next, mole of H2. We use 1.69 mole times of 2 mole H2 divided by 1 mole O2. We got 3.38 mole. Then, mass of H2. We use 3.38 mole times 2.02 G per mole and we got 3683 gram H2. The second one is mole to mass. The problem is how many grams of H2O from 0.27 mole CH3OH combustion. The equation is 2CH3OH plus 3O2. We got 2CO2 plus 4H2O. Then we need to search of mole H2O. We use 0.27 mole CH3OH times of 4 mole H2O divided by 2 mole CH3OH and we got 0.54 mole. Then for mass H2O, we use 0.54 mole times 18.02 G per mole. We got 9.73 gram of H2O. The third one is gas volume. So problem right now, volume of O2 at STP for 10L H2. So the equation right now is 2H2 plus O2, we got 2H2O. The first step, ratio. We know H2, the ratio is 2 mole and O2, 1 mole. So the volume of O2, we use 10 liter H2 times of 1 liter O2 divided by 2 liter H2 and we got 5.0 liter O2.
For this topic, we have two subtopics, which is limiting reactant and excess reagent. Limiting reactant, that means the reactant in a chemical reaction that limits the amount of product that can be formed entirely consumed during a chemical reaction. For the excess reagent, the meaning is the reactant in a chemical reaction that remains when a reaction stops when the limiting reactant is completely consumed. The excess reactant remains because there is nothing with which it can react. We change both reactant to moles. Ammonia is 2 grams, which is 0.1176 moles, and oxygen is 4 grams, which is 0.125 moles. Then we divide each value by each coefficient. Ammonia gives us 0.0294 and oxygen gives us 0.025. The smallest value is oxygen. So oxygen is the limiting reactant and ammonia is the excess reactant. To find the mass of nitric oxide produced, we use the mole ratio from the equation. 5 mole of oxygen produce 4 mole of nitric oxide. Using 0.125 moles of oxygen, we get 0.1 moles of nitric oxide. Then we multiply by the molar mass, 30 grams per mole. So the mass of nitric oxide produced is 3 grams. For the excess reactant remaining, we calculate how many moles of ammonia react. Using the ratio 0.125 moles of oxygen react with 0.1 moles of ammonia, we subtract that from the original, 0.1176 mole. So 0.0176 mole of ammonia remains. Then we multiply by the molar mass, 17 grams per mole, and the mass of excess ammonia left is 0.2992 grams. For this topic, there is two subtopics, which is theoretical yield and actual yield. The meaning of theoretical yield is the amount of product that would result if all the limiting reagents react. For the actual yield is the amount of product actually obtained from a reaction. How can we count the percent yield? With this formula, which is actual yield divided by theoretical yield times 100%. The actual yield is never excess than the theoretical yield. The theoretical yield is 0.8 grams and the actual yield is 0.77 grams. So we divide 0.77 by 0.8 and multiply by 100. And the percent yield is 96.25%. Molarity. The concentration of a solution expressed as mole of solute per liter of solution. The unit is mole liter minus 1, often written simply as M bigger. For example, 0.2 M sodium chloride. First, we find the number of moles by dividing 5.84 grams of sodium chloride by its molar mass, 58.44 grams per mole. That gives us 0.1 moles. Then, we divide the moles by the volume, 0.5 liter. So, the molarity is 0.2.